I'd like to thank you for all for coming, and I hope that you will have an enjoyable time with this presentation. I think there is a strong need to have people go out and get the message across that math is a fantastic thing to learn and to know, and that there's lots of benefits in knowing more mathematics. And I will talk about one aspect of that today. Let's see. So we'll start off with this. Why learn mathematics? Well, you may not have someone to help you, as demonstrated in this Calvin and Hobbes. Or you may go into a restaurant and bar and you may need to know math. Or when you die, I hope everyone can read that. So it says, okay, now listen up. Nobody gets in here without answering the following question. A train leaves Philadelphia at 1 p.m. It's traveling at 65 miles per hour. Another train leaves Denver at 4. Say, you need some paper? Okay. But actually, why learn math? So these are the reasons I come up with. One is it's intellectually stimulating. Mathematics teaches you problem-solving skills. Math gets you a job. And that is a really big thing. I am just amazed how many jobs are available with math background. It is probably in my opinion, of course I'm biased, but it is probably the major that you can get the most jobs in with mathematics. There are hundreds of jobs available. But that's a different talk that I'm not giving today. But the one I am giving is math is beautiful, which I think most of you will probably agree here. But I'll give you my perspective on that. Okay, so first, a puzzle, a problem. The shortest path connecting two dots, we know, is a short line, straight line. What's the shortest path connecting these 4 dots? Now, some of you have seen this before, and if you've seen it before, I don't want you to say the answer yet. But for those people who have never seen this problem, I want to get some responses. What do you think? If you've never seen this problem before, what do you think is the shortest path? I'll start off. I assume I can use this to write on the board. Okay, so if I have 4 dots, and let's say they're the vertices of a square, and the distance between the horizontal dots and the vertical dots is 1, I could make this path, and that would be 4 units. But that's definitely not the shortest path. Could someone explain to all of us how you could even make it shorter than this? Yeah, exactly. If you just erase one side, you still can travel from any dot to the other dots, and it's definitely shorter. 3. Okay. There is a shorter path. There are paths shorter than 3. Does anyone have a suggestion for a different path? Okay, well, 2 Steiner points. Okay, so you've seen the problem before. I don't want to get there yet. Somebody else, though, who's not seen maybe hasn't seen the problem or not quite familiar with the Steiner. X. X is a good common answer. And the value for x, what would be the length of that distance? Okay, 2 root 2, which is approximately 2 point. Okay, what I mean a path is, think of this as roads connecting 4 houses. So you can intersect it. They can intersect. The only requirement is that if you're at one point, you can travel to another point.
So we can use the intersection point as a turning point.
Yeah, right. So if you wanted to go from here to here, you would take this path. So these are the roads that are connecting this.
drive to get to a 4 points?
So what I mean by here in connecting these 4 points is if you're at any point, at any particular point, you can go to any other particular point. Okay. Okay, right. So I want there's an infinite number of paths that will do that. Which one of all those has the shortest length total? So again, you can think of it as maybe you have 4 houses, and you want to get a roads connecting them. What would be the least amount of pavement you would need to have to connect those roads? Yeah, there's different, when you get in graph theory, there's different ideas here. So, okay, this is really good. Better than this, but still not the best. Okay. All right, now, some people know the answer. Let's see, but let's look at this a little bit further. So, by the way, what do these all have in common? Straight lines, good. Yeah, sometimes people think, well, circles are good options, but if I had a circle, why would I know that that's not as good as this? Right, if I would just, this would be shorter than that, and so I could erase all those sides. So yeah, so they all have straight sides there. They're also letters of the alphabet, which shows that not everything that's a pattern is significant. Okay, so we've got that. Some people have suggested the Z, the X, and these are some relative lengths there. So what is the correct answer? Okay. Now, before we say that, we have to have a commercial break. Okay? So, our commercial break today is brought to you by sponsors from Calculus. What is Calculus? Now, usually when I give this talk, how many people here have not had calculus before? Okay, so we've got 3 people. Good. Okay, so you guys are safe from this, having to respond to this. All the rest of you could answer this. I'd like to give this question out to students. I thought there might be some students here. It's very interesting to hear how the students respond to this. One response I've heard is hard. Another is a response I cannot repeat. But let's see, what is calculus? Well, I would say the 2 main ideas of calculus are derivatives and integrals. And of course, there's the fundamental theorem of calculus, which is fundamental. So I mean, you emphasize this to the students, they don't quite always get it. It's like, this is the fundamental theorem of calculus, of course, shows that derivatives and integrals are related, although that originally when those ideas were talked about, they weren't. They weren't known to be related. And this is the fundamental theorem of calculus. You know, I point out to students, this is not so important theorem of calculus. It's not the end of the semester, I can forget this because, you know, it's not going to be on the final exam theorem. This is the fundamental theorem of calculus. It is a great thought, a great idea that goes along with all the other great ideas in the humanities. Also, calculus solves optimization problems, like shortest paths. And that's what we're going to be using it for today. Okay, back to our regular program. What is the shortest path connecting these 4 dots? Okay. Now, I like to do this. When I do this, I actually think this is a really important idea. It's a really neat idea. It's not so intuitive. So feel free to clap when you see the answer, to actually ooh and ah. I mean, this you know, it's not bad to vocalize our appreciation of mathematics. Okay, you ready? There's the answer, which is what you were going to say. Oh, okay, wait a second. Okay, wait. Let's go back again. That was not, I mean, I didn't hear Linda do anything back there, so come on. I thought you would. Let's try this again. Let's see if we can get a little bit more excitement about this, all right? So I'm going to show you, okay, with the retake, okay, say we're 2 minutes ago. I'm going to show you the solution to this. Feel free to, clap or say ooh and ah. Okay, you've never seen this solution before, but here it comes. Ready? There we go. Much better, much better. I appreciate that. Thank you. Okay. We're going to use a little bit of calculus. So this is going to be a little technical part here, but there's a reason I want to go over this. So I'll go over this kind of quickly. I did some calculations. I want to find the length of that path in red there. Now, I'm assuming that there is a solution. I'm assuming that the solution has this type of symmetry and that there is going to be this part in the middle that connects them, which are called Steiner points, as pointed out. And so in essence, we're just going to show what would be where would those those Steiner points be, okay? This isn't a proof that this is the best solution. It's just we're making a lot of assumptions here. But, it's going to get late if I were to go through all the details. So if I assume that that length is x, because of the symmetry, I can say that that's a half, and that's 1 minus x over 2. And using Pythagorean theorem, I can get that. By the way, Pythagorean theorem is also a great theorem. I have a daughter who is 11, and she's here with me and my wife and one of our other daughters in Washington, D.C. And one of the things that she really likes out here that we don't have in Utah is these American Girl doll stores. And she wants to buy something from there. So she's like bemoaning the fact that she couldn't earn money. Well, I thought this would be a great opportunity, so I am giving her a job. She is now working through AMC 8 exams. She's in 6th grade, but I figure this will be a good experience for her. And I'm paying her $5 an hour for working on these problems, as many as she wants to do. She finds out that they're hard, but she's sticking with it. And she had never seen the Pythagorean theorem before in school, which kind of surprised me. So I explained to her the Pythagorean theorem, which I think is a great theorem here. So using this, using the Pythagorean theorem, we figure out this length, and we can then have this function, and we can simplify it to be that. So using calculus, if we take the derivative of that, set it equal to 0, we get this. And we can then solve for x, and we get that value. And of course, that's not the final answer, because we're not looking for x, but we're looking for f of x. So we substitute that back in, and we get 1 plus square root of 3, which is approximately 2.73, which is better than this. Now, this is kind of interesting in one aspect, because I could have made this u into an h, and that would still have the same value of 3. And you could kind of see that this h, if I were to take these 2 points, if they were movable, and bring them closer together, if I brought them all the way in the middle, I'd get this x. But if I stop somewhere in between, I get this better solution there. And that might be surprising to some people, because that solution in the middle is better than this solution or this solution. All right. One other aspect that's interesting is I want to figure out this angle theta here. So I notice that the sine of theta is equal to that, which simplifies square root of 3 over 2. So theta is 60 degrees. Therefore, in this particular case, the lines meet at 120 degrees angles. And that's what is significant. Now, this is a very hands-on presentation. I'm not sure the MAA is used to this. They agreed to have this little covering here to protect the surfaces. So a couple weeks ago, I made this little plate here, went to Home Depot, and I just happened to have with me today this bucket filled with soap solution, water, and some glycerin. And we're going to dip this in here and see what happens, see the soap shape that comes out when we dip this. Okay, so let's see if this will work. We have to jiggle it a little bit so that we get stable solution. Oops, got a bubble in there. That doesn't help. All right. So I don't know how well you can see that. But yeah, it could, right. And why is it sinking? Of course, right. It's sinking because of gravity playing on it. Yeah, it'll move. Yeah, if I were able to lay it flat, but of course then you wouldn't be able to see it very well. So yeah. So anyway. Oh yes, thank you. Okay, so when I do this, I like to ask students, and I think it's good for all of us, how can we generalize this problem? Well, there's several ways we could generalize it. What, were you going to mention one? Oh, okay, good. So maybe summarizing that in maybe a little different perspective, I could change the number of points and the location of the points is another way of thinking about it. And so that's one way I want to do this. Move some of the points around. So, for example, what's the same problem if I move, instead of having the 4 points on the vertices of a square, if I move the bottom points up, so now I have a non-square rectangle. And I just have this, happen to have this. So let's see if this one works. Okay, again, it's a little wet here, but I don't know if you can. I don't know if that helps you see it or not. Probably not. It does. Okay. Yeah. So the one thing you can notice here is that the angles, again, between these points that are put in here, Steiner points, remain 120 degrees. Again, this is just a model of it. It's not totally accurate, but it's a good approximation of it. Okay. And going on that same idea that was mentioned, I can increase the number of points. So I could have this. So based on all that you've learned so far, I want you to visualize in your mind in the next 5 seconds what would be the shortest path connecting those 5 points. Ready? 5, 4, 3, 2, 1. Lock in your choices. Everyone's got an answer? There you go. Okay. So again, the idea is you have 120 degrees. And I have another one here. I'm not going to do this now, but afterwards, if you'd like to come up and have some good, clean fun, feel free. Okay. Another way I could generalize this, there's lots of ways to generalize this. And that's what makes math so exciting. You can generalize problems, create new math ideas.
Does that work for any variables, or is there some initial conditions that matter?
There are some initial conditions that matter. Yeah, that you'll get. You won't always get 120 degrees. For example, if I had 3 points that were like this, the shortest path will just be like that. Or you can even think of it, if I have 3 points in a straight line, I'm not going to have a 120 degree angle. So that was a good question. We could talk about that afterwards. We can go a little bit different than the direction I want to go. Okay, so now, though, another way to generalize this is go up a dimension. So what's the analog of the Steiner problem in 1 dimension higher? So Steiner problem, the problem we've been dealing with, minimizes distance in a plane. So it's a 1-dimensional object in a 2-dimensional world. So going up a dimension, 2-dimensional object in a 3-dimensional world. So I'm minimizing area in space. And what does that? Well, soap films. That's why I'm here. Okay. So here is my three-dimensional, going up my two-dimensional object in a three-dimensional world. I'm going to dip this in to the bucket here, pull it out, and it's going to come up with a soap film. Now I want you to visualize in your mind what you think this is going to look like when I pull this out. Now some responses, when I've asked students this, some common responses are it's going to look like a box, flat at sides. Okay, some of you are not agreeing with that. That's good. Some people feel that, some students have suggested that there's going to be like a little cube in the middle, and there's going to be little edges that'll meet with the cube in the middle. Okay. Some people have said it will kind of bulge out like this, like a balloon. And some people have said, oh, well, I'll leave it at those. Okay. But so think about those options. I did give this talk once at a prestigious university in the Midwest where a student said it was going to look like Venus de Milo. I'm not sure where that came from, but must have had it came from a humanities class or something. Okay, I'm going to dip this in, pull it out, see if it matches with any of those or what you think it will be. Okay. Here we go. Let's see if I can bring it over here. Maybe you can see it a little bit better. Yeah. So it's pretty much a saddle surface. You see that? Bending. Going like this. What, yeah. Yeah.
It's significant that it's a single sort of a closed path among the vertices, right? And that there are no extra edges in there.
Well, at the end of my talk, you can come up here. I have some things that are made up already that I'm not going to demonstrate what they are. If you feel free to come up here afterwards and play with these and make some conjectures, ideas. And I just got today in the mail that my wife brought to me. So on the way to the talk with some more of these zone tools if you want to play with them. So lots of fun things you can do with these. I am going to demonstrate a few more, but not that idea yet. So here's one more. Okay. Slinky. I'm going to dip this in. What do you think it's going to look like? Ideas. Okay, good. Spiral staircase. Right. You could say something, or a cylinder. Okay, like on the outside there, holding those in. Yeah. Okay. Good. All right. Any other ideas? So this is to me. Sometimes people, when they think of mathematics, they think of it as like it's you don't really think about the problems. You just know the answer. Or you don't know the answer. And for me, doing mathematics, I think about the things, and sometimes I'm wrong, sometimes I'm right. So it's good to ask questions and explore. And if you're wrong, it's okay. Learn from it and see what you can do. Okay. Well, when we dip this in, it looks like this. So see how well this shows up. So I've heard this described as a spiral staircase, a rotini pasta noodle, a corkscrew. So, and it popped. Okay. What's that? Yeah, maybe the shadow is good. Yeah, I'll try it one more time. Can you see the shadow?
That sort of shows where the
All right. We have 2 rings here. I really would like someday to get rings that I can just kind of like go like this and they act like I'm a magician, Art Benjamin or something. But I'm not at that class yet. So 2 rings here. I'm going to dip these in. What is it going to look like when I pull these out? I'll pull them both out at the same time. No, they'll be apart. Finger? Oh. Oh. Yeah, so kind of goes in and then, yeah. Okay. Okay, good. Any other ideas? Well, let's try. Well, here's one solution. They're just 2 separate discs. Okay. So that happens, and that goes to what you were asking about together. I don't know if you can see this, how well you can see this. And then I do that. I pull them apart. It is kind of like that finger, Chinese finger. And I can pull them slowly farther apart, but then I'll get back to the other solution. Okay. And of course, this is a fun thing in calculus because you can talk about this in terms of a chain. Okay. So if you have a chain which mathematically can be described as a catenary, which can be described by a function of the hyperbolic cosine. And if you rotate that around an axis, you take your catenary becomes a catenoid, which is this shape here.
So it's not a hyperbola,
It's a catenoid, yeah. And so this is really fun. I do this in my calculus classes, and I talk about my research with minimal surfaces, and then I recruit students to do undergraduate research with me on this stuff. So, by the way, okay, so Michael made a little plug for the book. I should mention all this stuff that I'm talking about pretty much is in the book, in my chapter in the book. So, and there's lots of problems in there. We wrote that for problems so students or people kind of new to the field could investigate things. So it's a very investigative type of approach. All right, one last one I'm going to do is this. I'm going to dip this cube in there, pull it out. Now don't say what the answer is, but think in your mind, what is this going to look like when I pull this out? Okay. Everyone have a decision made? Okay. All right. Here we go. Oops. Got a little bubble in there. Got another bubble in there. Okay. So, I don't know if you can see this. Yeah, you can ooh and ah with this one. Clap if you want to. Let's see, if I put it over here, I don't know if those people...
Yeah, the shadow, again, the shadow.
So, as you can see, it is the analog of the problem that we talked at the beginning, which it should be, right? That's what we were thinking it would be. Okay. All right. So, just a little... What's that? Then the square? Oh, this had more symmetry than the square?
The soap film had less symmetry than the cube that we started off.
Oh, yes, right. Because it's an approximation, and it doesn't not quite totally flat the edges. Also, so right. So soap films model surfaces that that minimize area and space. You've got this meniscus idea when you have a drop of water on there. The water molecules, the oxygen molecules, are pulled toward the center, toward each other, and so you get that little bulging there. Surface tension tends to minimize the surface area of a shape, and soap solution has the same property as water, but works better because it has a lower surface tension and it evaporates more slowly. So I guess theoretically you could do all this with just pure water. But the evaporation rate makes it hard for the bubble to last. Okay, so let's look at this a little bit closer, this connection between the two. A line connecting 2 points, so that's the shortest path touching the points. It minimizes distance. It has zero curvature or bending. Minimizing area, we have a surface connecting a frame, like that. It's the smallest covering touching the frame. It minimizes area, and it has zero average bending. You have to have some bending there if you have a frame like that. So, but we could talk about zero average bending, and I'll talk about that a little bit more. All right. This idea, this modeling in 3 dimensions, is called minimal surfaces. They minimize area locally. They look like saddle surfaces, just like we had for this one. Remember we had the saddle. So at each point, bending upward in one direction is matched with bending downward in an orthogonal direction. And here's some images of some minimal surfaces. This is the catenoid. Okay, again, if we had those 2 rings and put one on top of the other and looked at the soap film, we get that. Here's the helicoid that is modeled by this shape. There's Enneper's surface, which is like a Pringle potato chip. Okay. Shirk's doubly periodic, which is modeled by this. And we have Shirk's singly periodic and Costa-Hoffmann-Meek surface. And I want to show you this. So this is an example of a Costa minimal surface. And what I like about this was made by a 3D printer. So I don't know how many people have seen something by a 3D printer, but so the way a 3D printer works is you have this powder, and you have a head that goes back and forth over the powder. And as it goes over it, the equations you put in tells it when to bond things together. And as you do this, then the powder moves up, and you can build the surface on different levels. And so this is a model of a minimal surface, and you can see through it. You can go through a hole here, come out through that end, and do this. And for a long time, the known minimal surfaces were just a handful. The ones that we've talked about, the catenoid, the helicoid, Shirk's surfaces, Enneper's. And in I think it was 1984, Costa in Brazil, for his PhD thesis, came up with this surface. And since that time, and with the advent of computers,
The frame is are the 3 circles?
yeah, I don't know what the frame would be. You have those 3 circles, but you're going to have to do some jiggling there to get these holes.
The surface is intended to go out from the end, right?
Right, so that's a caveat here too. All these surfaces go off to infinity. When we do, for example, the catenoid here, I mean this is a finite representation of it. In essence, it goes off to infinity at both ends. But the board wasn't large enough to represent that, so we had to do it this way. Okay. So
Same with the Costa-Hoffmann-Meek, so it goes off to infinity also.
yeah, yeah,
This way.
right. And so since those surfaces have been discovered, there's now hundreds of new surfaces that are being discovered, and the idea is try to classify these and connect these surfaces. So let me go a little bit into the mathematics behind here. So differential geometry combines calculus with geometry, allows you to study these things. So if you have a surface, it can be parameterized by a function with 3 coordinates. If we're in R3, to define a parameterization of a surface. And at each point of that surface, there is a unit normal. So that normal is pointing up. So for example, if this happens to be my surface, and this is a unit normal, it's a vector that's pointing straight up, depending on where it is on the surface. And if I have this normal pointing up, I could lay a plane or a piece of paper that would contain this normal or this pencil, and that piece of paper then would intersect the surface, and it intersects it in a curve. I can move the piece of paper around so it intersects it this way, that way, infinite number of ways. And so in doing that, each of those, if we have this curve, each of those curves on the surface has a curvature value. And as I move that plane that contains that pencil or the normal around, I have a continuous function of curvature values. And if I'll let K1 be my maximum and K2 be my minimum curvature values at that point. And so we define the mean curvature, mean not angry, but average curvature of it to be the sum of those, the average of those two, the sum divided by 2 of the maximum and minimum curvature. And a minimal surface then is defined just to be a surface so that the mean curvature is 0 at every point.
How do you know there's a maximum min?
Because I have a continuous function in that dimension. Let's see, so I'm just dealing in R3. I know that there's going to be a solution. There's going to be at least one curve intersecting it there, and as I rotate that around, I'll have an
Just function 0 to 2 pi.
yeah, because you're rotating it around from 0 to 2 pi. Yeah. But those are good questions to ask in geometric analysis, because sometimes, I know, like when Frank Morgan worked on some of the bubble problems, wasn't certain whether there is a solution or not. So you need to prove that in many of those types of problems. Okay. So again, minimal surfaces minimize area locally, look like saddle surfaces. So again, the bending in one direction, if you look at the perpendicular direction, the bending, that's going to offset it. And again, we had those as examples. So lines minimize distance and have 0 curvature. Minimal surfaces minimize area and have 0 average curvature or mean curvature. And the goal is to better understand minimal surfaces and their properties. So how can we continuously one question is, how can we continuously transform a minimal surface into another minimal surface? How are these surfaces connected? So let me give you an example. So I had some undergraduate students work on this problem, connecting any per surface to a sheet of the helicoid. So the helicoid, again, is this one that looks like the spiral staircase. If I take one sheet of it, it looks like a strip part of it. So here's a visualization of it. So there's the any per surface. Then you get a sheet of the helicoid. And I think this is just really cool. The undergraduate students were able to do this. What happens here is everything's a minimal surface in between. There are certain conditions. I left a lot of these off. What's happening here, if anyone knows some background about minimal surfaces, these can be described by their Gauss map. And in this case, the Gauss map is the same for the two surfaces. And there's one other property that has to hold true, but in that case, you can deform one into the other. And so there is this connection, this family of surfaces that you can do this for. Another one, it's kind of interesting here. Shirk's doubly periodic surface. Now, that was the surface that was formed by this shape. We call it Shirk's doubly periodic. Why is it called Shirk's doubly periodic? Well, doubly periodic means that it repeats. And this is one piece of a larger surface. Not only does it go off into infinity up and down with these sheets, but it also can be repeated like a checkerboard. And from above, it could look like this. So here is one copy of the surface looked at above. And then diagonally here, here's another piece put to it, another, another, and another. And so I could put 5 of these frames together, dip them in soap solution, and I would get a larger component of Shirk's doubly periodic. It can go forever in the horizontal direction or the vertical direction. All right, so what would happen if we were to basically grab that end and that end? So the upper right hand end and the lower bottom left hand end, and started pulling them apart. What would happen to the surface? Any ideas? Well, let's see. There's a start of it. So I'm, again, pulling this part kind of up. This part's pulling up. And as I do that, everything has to move in accordance so that it keeps the minimal surface, the mean curvature equal to 0 property holding. Okay? So if I keep pulling them up, it goes off like this. And in the end, I get that. And what does that turn out to be? Right, okay, yeah, it's up there. 3 sheets of the helicoid. All right, so here's a side view of it. There's 5 pieces of Shirk's doubly periodic. I'm pulling them apart, and I get that. I think it's just really cool that you can do this. And theoretically, you could do this with soap films. But I have no idea how you would do this. But I think it's just cool that you can do this, and you can preserve certain properties, mathematical properties, as you do this. Here's another really neat idea. We're going to change the catenoid into a helicoid. And in doing this, I'm going to demonstrate one of the applets that comes with the book. The applets actually are online for free. But this is an applet we designed to help people kind of visualize these things. If you're at a university, you might have access to Maple or Mathematica or MATLAB, but this is a free applet that lets you do that. So it's a little video I made from my computer. So those are different tabs. I'm going to pull on that, and I've got some predefined functions. So I'm going to pick one, and this is going to be the helicoid, I believe. Yep. And I can rotate it around. Part of the helicoid. Okay, now we're going to go demonstrate what the catenoid. And move that around a little bit so you can see that. Rotate that. And then we're going to go over here, this button here. If you click onto that button, it allows me to transform the catenoid into the helicoid. So there's a helicoid, and now it's going back into a catenoid, back into a helicoid, and back into a catenoid. And so not only, I think, is this beautiful, but it keeps some really nice mathematical properties. One of the properties is that if I were to draw a normal vector, so like a line emitting from the surface, so somewhat perpendicular to the surface, if I were to draw that, all those phases, as I go from one surface to the other in this case, the normal would continue to point in the same direction and wouldn't move. As I made all those transformations, the normal always points in the same direction while it goes through that whole set. There are other properties that are just, I think, really cool about this type of transformation. Okay, and a new surface. So this past year, I had some students working on something, and we have what we think is a new surface, new minimal surface. We're not sure what it is. It has kind of this helicoid end here. But on the ends of it, it has kind of like a wavy part, almost like anapers. But as you can see here, they get smaller and smaller as I go farther along. And then over here, we have something that we're not quite sure what happens to it. I've asked some people in minimal surface theory if they've seen a surface like this, and they said they haven't. What we need to do now is to figure out what are the interesting properties of this and what class of families would it be categorized in. Again, you've got all these surfaces. You're trying to put them in different categories so to try to find a way to represent the different families and how they're connected. And what's it? Is it a fractal? I don't think so. Yeah, I mean, this part, yeah, it does kind of go on and on. There is a minimal surface called the wavy plane, which is if you were to take an anapur surface and open it up, so kind of like make a cut from the end to the middle, and then open up that cut and expand the one middle part out, you get a plane. And then if you kind of multiply it, you get a wavy part that goes on forever. So this kind of has that property, except here the waves get smaller as you go farther along. And we've used a really complicated function here to represent it. It's a singular inner function. So it has certain properties that make it very complicated. A lot of these functions are represented by things. You have a Gauss map that maybe looks like z to the end. And here, the Gauss map is something like this. Yeah. Much more complicated, which would make sense why people haven't looked at it. But it's great to have students. I mean, they've got great computer skills, and they can look at this. So I have a Skype meeting with them tomorrow to see what progress they've made on that. So anyway, I think these are just really cool things that you can do with mathematics, these different shapes and the way they're connected. So again, why learn mathematics? It's beautiful. Okay, thank you.